let's start with this first topic. You will notice one difficulty just over the day. The three talks, as I said, are related. They are not the same, but they are related in the topics. But these are different papers, and the notation is different. And so, what you will notice, well, the next talk I will switch completely notation. And I hope it's not such a big problem. But it's something that's, of course, a little bit annoying, but this is related to the fact that these are based on different papers. And of course, I prefer in one paper you have a notation, yeah, to be consistent there, and then the next paper we change. Okay, so it's a little bit of a problem. So the first thing, this is the oldest paper I present today. From the 5 papers I present today and tomorrow, 4 have been published, only 1 is just under revision. This one is a paper who has appeared in JASA. It's a discussion paper in 2001, so that's the oldest one in this topic. But perhaps it's quite good because, as an introduction to this type of functional principal component analysis, because it's, well, some simple context. So, and it's a joint work with Klaus Ruttikau. So, what's the problem I consider in this paper? It's something that you have something like, you want to compare different densities, different distributions. So what you have here, you have something like capital T different populations. And for each population, you have a number, which I call NT of observations, which I call x1t to xntt. And each of the x's in each t, you have a density f of t. And so what you have here, you have capital T different densities, f1 and 2ft. So you have essentially what we call density family. So it's not one population, but it's a multiple population problem. Now what we're interested in, say, very often in standard parametric statistics, there's a problem, are all these distributions, the underlying distributions, you have capital T different populations, are distributions identical? Are they different? Well, usually most applications they will be different. And essentially all tests you will assume essentially here, you assume if the NT, the number of observations from the underlying population is large, well, tests of equality of the population will always be rejected. Okay, so the examples I have in mind here is something like this is what's about income and the age of households. And we use the FES data, Family Expenditure Survey. That's a type of big data source from Great Britain, where in each year they draw a sample of approximately 7,000 households. And for each household they record income and age of the head of the household and say expenditures for several commodities and so on and so on. Many different variables. And what we're interested here is just income. So these are just income distributions, income densities. And we also consider age densities, age of head of household. Head of household is defined as the person who pays the rent. And so what you have here is something like the NT, the N, the number of observations per year. This is something like 7,000. And the T here is just the index for a specific year, 1960, 1961, 62, 63. And so the essential problem is you have, for example, income densities for different years, and you want to compare them. And are they the same all the time? Are they different? If they are different, how do they evolve? That's the main problem. So the main focus here is not to say, well, just to test these things are identical. They are not. That's why 7,000 observations, every test that say, oh, the income distribution doesn't change over time, will reject. P-value 10 to the minus 40. Okay? But the thing is then to get more information and to see how do these things evolve. So just to show you some pictures here. For example, what you see here, these are estimated income densities over something like 20 years. So each line here is an income density from Great Britain for a specific year, and just you have several curves here. These are several years. just to see a little bit of scale, you see here the scaling is 1, 0, 1, 5. We use what is called mean scaled income densities. That means for each year the incomes are divided by the mean income, and so someone with this income equal to 1 will have just a mean income in the specific year, and 2 is twice mean income, and 0.5 is half. And so you see a typical structure of income densities, which is there are only few households which are extremely poor, have nothing, can't survive. Okay. Then there are a lot of quite poor people who have income much less than half of the mean. These are essentially the pensioners and unemployed persons. And then there's goes down again, and here's something like a middle class peak, just full-time employed workers, for example. Yeah, and then there's of course a big tail. There are of course quite a number of rich people. And the other thing, this is the same with age densities, the age of the head of the household for different years. We see that's a little bit chaotic, these things. Yeah, you must not say, this is different from the age distribution, the age density of the whole population. This is the head of the household, person who pays rent. And of course, it's very rare that the 15-year-old is the head of a household. Right? So it doesn't represent really the age distribution in the whole population. Only say head of household. And well, the task is a little bit to see. These are kernel estimated densities, to see, well, get some structure, development over time, and to see how these things evolve, and what are, say, the major components of this evolution. And what we do here, just to try to characterize the evolution of such an income distribution, income densities here over time in this context, is we use functional principal component analysis, which I will abbreviate with FPCA. And well, you all know classical principal component analysis, who identifies principal components explaining the variability of a sample of random vectors by calculating eigenvectors of the empirical covariance matrix. That's very well known. And functional principal component analysis, well, there you have, instead of vectors, you have functions which you analyze. And you then use, and then the covariance matrix becomes what is called a covariance operator. That's, well, dimension increases, gets infinite, and so a matrix becomes an operator in a way. And it determines eigenfunctions. These are just, of course, these are functions, no longer vectors, and the corresponding eigenvalues of the empirical covariance operator. This is something that is very often applied in functional data analysis. It's one of the basic tools, and as well from a practical application as from a theoretical side. It's much more important here in this world than in the world of multivariate analysis, where, say, usually principal component analysis is just a descriptive tool, which is sometimes used, often not used, but here it's much, much, much more important. And it's also one of the most important things for theoretical analysis. Why is it more important? Well, the point is a little bit that if you, for example, in multivariate analysis, if you calculate principal components, very often if you have just a vector of different variables, it's very often, for example, very hard to explain, just to interpret what's the functional component. It's a very hard thing, and usually it's based on vague ideas, correlation with the original variables and so on. This is something that's no problem here, because it's just something like, this gives you, because the principal components gives you something like a basis expansion of your random functions, and not only some basis expansion, but a basis expansion with, in a certain sense, the best possible basis. And just to give you a little bit of background of that, this is new in this talk. I've introduced it to give you some idea of this functional principal component analysis and the so-called Kaun-Lev decomposition, which is often cited in the rest of the talks, but never really explained in detail, so I want to do it here a little bit. So the problem is a little bit of notation, because on all the rest, everything you will see in functional data analysis, all papers who use that, the F's, which are in this application here, densities, will be called X, which are just random functions. And the T, that's a number of functions you have will usually be n. So it's a little bit different of notations because of these particular applications where these are densities over time. But usually these are just some observed curves, maybe not densities but something completely different. You will see different things in these talks. And then it's called x and n. So later on we also denote it by x and n. And so we generally have something like an observed random functions. Well, it may not be densities, but well, another thing, for example, which we used just recent application was something like ozone pollution curves over a day. Yeah, so for example, you have a day of observation of the ozone levels recorded on a continuous time scale. Yeah, from midnight to midnight. Okay, and this is one curve, and you have different days, for example. Or there are many other examples. And if you have something like a IID, if these are random functions which are identically distributed with the same distribution in generic f, and these are second-order variables, so that the integral over the expectation of the squared variable exists. And then what you define here is something like the covariance operator of this random functions. This is not something that is in the context of our income density. It makes a lot of sense because these are just income density of over different years. This is not an IID sample. This is something, there may be stochastics in it, but it's not you can't say that these are independent. The income density of 68 and 69 are not independent. Okay? So, but that's just to give you the general context. And so for these samples of curves, what you can define is then just for vectors you have the covariance matrix, here is the covariance operator, which is of course it's more harder to define because it's just not a square rectangular scheme of just values. Usually it's defined like that. It's something gamma psi of if you a covariance operator. An operator is something where if you just apply the operator to a certain function, which you call psi, you get out another function, right? I mean, another operator is a differential operator. You add a function x, adds out another function, in this case a constant, yeah? Or x squared, and gives you x. And so this is the covariance operator, and it's a very simple operator. It's just say something what you have here, an integral over sigma y z times this function psi of z dz. And you see this gives a function in y. And the sigma y z is what we call the covariance function. These are just a generalization of the covariances for the different variables in a multivariate context. It's only here, of course, these are continuous variables. These are not just in some indices. What you see is just the expectation of fy minus f mu, that's the mean. Fz minus f mu for different values of y and z. Okay? You have a certain domain, say 0, 1. And so the y is from 0, 1 and the z is from 0.
So, now we are in a function space, right? Before that you were in some kind of vector space.
Right, yeah.
On a screen, on a computer screen, you're always in a vector space because you have, say, capital N pixels, right?
Yeah, sure.
So why are you using now continuous notation, that means function spaces, instead of staying in Rn?
Simply because you have more means to analyze that. Usually, I mean, of course you can say everything is discrete. That's true. I mean, but it usually doesn't help. It's just to say it complicates things more. Here in this continuous space, you have much more properties you can use than just functional data analysis. Is not just say analysis of very high dimensional vectors. Very high dimensional vectors have no structure. Functions do have structure. They may be continuous. They may be differentiable. And so on. Vectors are never continuous and differentiable.
No, but you
Oh well, this makes a big difference. What you want to do...
then you have some kind of features.
Well, I mean, then you already have a functional interpretation. If you have something, if different elements of the vector have some types of Lipschitz continuity, then it's already some functional interpretation, right? This is just the way to put it to get some theoretical results. Where just later on you can do very simple discretizations of that, and essentially it's not very difficult. You just have to get used to it. Because, well, this is an operator, but it's the simplest version of an operator that exists. It's what is called a Hilbert-Schmidt operator, and essentially it's something like a very high infinite dimensional matrix. It's all properties. There are other operators which are much more complicated, which have continuous, well, even the differential operator is much more complicated. As a continuous spectrum. This one has a discrete spectrum. Right? So this is something like, you can always think here of very high dimensional big covariance matrices. Okay? And just, if you want to do any theory, this is something that gives you the basis to do it in this context. Because there you have properties which you can use.
At the end of the day, you get some eigenfunctions of this covariance.
Right. You can show this operator here, at least if you assume what's always assumed, that the sigma is continuous in Y and Z.
Okay, so but what are the natural eigenfunctions for?
There are no natural eigenfunctions. It completely depends on the structure of the sample. Because this is what you call the coronal F decomposition. What you get from that. And that's an important thing. That's always cited from that. That you have here a sample function ft. Well, they are all IID from this point of view. That's the mean. But now you can expand it in, say, as a linear combination of these eigenfunctions, which are also called principal components, functional principal components, the same thing. The eigenfunctions of the covariance operator, functional principal components are the same thing. Okay? And so you can just represent as linear combination, and well, these thetas are just the coefficients of this linear combination. This is called the coronal F decomposition.
Here you already assume that you have the same structure of covariance operator for different random elements for different densities.
No, I mean, I wanted just to give a little bit of the context. This does not apply to the kind of density context. Okay? This is not true in the context which I presented for these income densities, because this is not IID data. Right? However, for the income densities, what is done, just always to say it, you can always do it on the empirical level. I mean, if you have just T functions, replace the expectations by sample means. Then you have the empirical covariance operator. And this you can always define. Right? Then it's not necessary that these are.
So what I'm asking about, so in your decomposition, only coefficients depend on T, but the eigenfunctions not.
Right.
So this is already a kind of assumption.
This is a kind of assumption if you have a time series, for example. I mean, usually this is considered IID data, and then it's not an assumption. That's like that.
Okay.
Yeah. But in context of time series, it's an assumption. Yes, absolutely. Oh no, that's the wrong way. Okay. So this is the coronal F decomposition with its coefficients theta. And what you have here, the theta just, well, you get by integrating the gammas with the f's. So this is an individual score, the function principal component score, a real value in this case, right? And so essentially you see the gammas in these things are, of course, the fixed eigenfunctions. These are not random, these are just determined by the underlying structures. So the random expected is a random curve. All randomness is now in the thetas, in these coefficients. There's the randomness. These are random variables. And they always have, in this context, they have expectation 0, and the variance of the thetas is always equal to the eigenvalue, to lambda r, to the r corresponding to the r principal component, and they are uncorrelated. If you assume this is a Gaussian process, so there's something like normal distribution underlying, they are even independent. So for different r and s, different here they are uncorrelated, or under the Gaussian assumption always independent. What you also can show that the sum of the eigenvalues necessarily here in this case, because it's a second order variable, is bounded, is smaller than infinity. And the big thing is that very often, so these lambda, these eigenvalues, they fall off quite rapidly. And so what you get here, that in order to get a good approximations of your curve, of the FTs, you may not need to go to infinity, but say with 5, 6, 7 components, you may already have explained a lot, say 99% of the variance of the Fs. So very often, without losing much, you can here stop at something like 5, 6, 7. But it of course depends on the particular problem you have. And what you also see, it corresponds to what we usually do in non-parametric statistics. Very often, at least, we consider basis expansions of our unknown functions. This is a very particular basis. This is the basis where the gammas, the basis function, correspond to these eigenfunctions of the covariance operator. It's not just a Fourier basis or a spline basis or something. It's not a fixed basis, but the gammas are the gammas which are eigenfunctions of the covariance operator. So this is an expansion in terms of these principal components. This has special properties. First of all, you see, for example, coefficients are uncorrelated, and this is essentially the only basis where this can be assured. Usually, if you have Fourier coefficients for different frequencies, the coefficients will not be uncorrelated for the random curves. And what's more important is just if you think of approximating curves by, say, linear combination by basis functions, this provides the best possible basis, the best basis properties of this cohen-Loeffler composition. What you can show, that's not very hard to show, is that if you just now consider the first L components here, L is equal to 2, 3, 4, 5, and now you consider the best possible basis to approximate your functions f by, by 5 basis functions, by L equal to 5 basis functions. Then the best approximation with the minimum L2 error is just given by these gammas, by the principal components. So it's something that has a sparseness property. If you just have with 3 components, it gives you the best possible approximation of your functions f with a basis which only consists of 3 components.
But of course, if you this is not a density. If you truncate expansion, it's not a density. And it's not any more density if you truncate it.
Well, okay. I mean, this general context. Well, is of course for densities. It is possible in the sense, but of course in this case there will be restrictions, implicit restrictions for the parameters. I mean, usually in this case, if you consider with densities, the problem would just be the positivity. That would be the problem. Not the integrating to 1, because this is the mean density, and the integral of over this will be 0. Okay, but the positivity will be a problem, which will impose particular restrictions to the thetas. Right? So for densities, it's some too, but they say there are some drawbacks using that for densities. That's true. Okay, but I mean, I just wanted to tell you these are the important things. These are not only used in terms of densities. This is just one particular application. Okay, and it's not perhaps also the most, but this is a very special basis. And the really important thing is that it gives you a mean to approximate your functions by very few basis functions. If you use, for example, you could also approximate your f's by a Fourier basis or something like that. But for example, to get good approximations, you will need something like 60, 70 components. But perhaps with this gamma, you only need 3 or 4. Because this gives the best possible. So this best basis property is the essential thing. Okay. Now here in this context, of course, we apply it to these density things. Here just some literature on these things. Okay, it is not complete, not at all. There are many others. You have a normal distribution, but you have to fix that. This gives you the particular Wiener process, fixing the sigma. And if you know the sigma, you know everything about the process. So everything else. But of course, the sigma is everything is possible. In principle, you could have a Wiener process with any possible gamma. In case of Brownian motions, you will have a Fourier basis, but that's a particular thing. Okay, so for these density families, what I do here is essentially these are, though they are random functions, they're certainly not IID random functions. And so however, what we want to do a little bit is to get something like, the idea was just to have some type of a mixture model. Say just as income densities, well, essentially they are a mixture of different subpopulations, the unemployed and the pensioners and the full-time employed and so on, which all have different income types distribution. So essentially they are something like a mixture distribution, mixture of different densities. And if you say something like a finite mixture, at least you can rewrite it in this context, that you would say that you would try to expand something like the FT is the mean over all the time, and some component which I call the theta dj gj. And the g would be something, principal components, which add something over time. The advantage of this type of decomposition is that it would give you something like the g's would be basic functional structures, and the theta t would say how does it vary over time. So you could interpret these basic functional structures, the g's, how do they look like, how is the time evolution of the thetas, and to say how do the densities evolve over time. That would be the basic idea here. And so essentially what we could do, what is always well defined, is not just using this theoretical covariance operator, which in this case doesn't really exist very well, which is not quite clear, but to do something like an empirical covariance operator with the empirical covariance function, which just where you replace, compared to what I've done above, the expectations by means, and just integrate over that. What we additionally here consider a little bit of modification, we additionally add a weight function, because we consider densities. The weight function is a little bit there, because densities go up and down, they have a tail, tails are small, and just if you look something like the L2 norm, only say that the center of the densities would count. And the weight is a little bit there just to give more weight to the tails. That also these tails are a little bit well modeled. So this is, of course, this is just a change of norm. Yeah, instead of the usual L2 norm, you have a weighted one. And the structural model will be, it's a little bit just that you try to expand the f's with type of basis functions. For some L less or equal t, you have this decomposition, it's f mu plus some parameters which modify the gj. As I said, as you already said, with densities the problem is a little bit in this decomposition, the positivity, that in order that this is a density, you have really implicit restrictions on the structure of the thetas. How do these develop, essentially, to get some tendency, to understand a little bit what is the basic development. Of course, one of the big assumptions here is that there is a basic development, that there is not just some chaotic development from one to the other. Well, I'll show you later on what comes out. In the case of this British income density, it's quite well interpretable. I'll show you later. Okay? But essentially, the idea is that you want to get a sparse description of the f's in terms of some type of basis functions. The mean and some basis functions where the time development is just in some parameters theta, which we may analyze.
Why there should be only finitely many non-zero eigenvalues? Because in fact they can just decrease to zero. And
well, in this case,
or this kind of assumption of truncation of this.
First of all, this is something like, I call it a structural model. So it's a type of assumption that you have something infinite number surfaces. So this is quite often used now in application in different contexts, where you say, well, okay, that's a structural assumption. I don't know L. Yeah, I don't know how large it is, but there's a finite number of surfaces, which simplifies life. Yeah? May work well, may work not well. In this context, it's not really an assumption, because it's an empirical one, and this covariance operator has at most t non-zero eigenvalues. It's an empirical one. The theoretical one will have infinitely many, but here you can go no farther than t. So, in principle, it's not yet an assumption. It's only an assumption if you say if t increases, L does not increase or something. Then it becomes an assumption. L is fixed as t increases. Okay, then it's an assumption, but not yet. Okay, and of course also empirically you have the best basis property. So you want here the best description in terms of these basis developments. Okay? So, and what we do is a little bit inference about the GR and theta and about the dimensional L from the given data. And we look for a procedure that allows efficient estimation of the G and evaluate asymptotic distributions, and then also determine a little bit how big is L. How far can we go? And how how many functions do we need to approximate the densities very well. And of course, if we need a lot, then we are dead. Then we can't interpret a lot. Then we can't interpret a lot. However, if few suffice, it's fine. And our idea is, well, of course, what you do here. The problem is, of course, what you have not yet thought about is, of course, you don't observe the f's. These are densities. You always have to estimate the densities from data. So there's an estimation error, right? You don't know the f's. If you know the f's, you could compute everything immediately. But you don't know the f's. You have to estimate that from data. And so the idea is, well, it wouldn't really be very important to analyze something that's a component whose influence is smaller than, say, the error level. And so you go only as far if you add an additional component, because the importance will decrease and decrease. And if the importance of a component is so small, doesn't go above the error level, then it's not important. Okay? Oh, somewhat to the W also, I forgot to say that what we choose here is W is something like 1 over fu of x. That's our weighting function, which gives a little bit more weight to the tails, so that they are also represented appropriately. Okay, so that's what we try to do. And testing hypothesis of this form, and our method for determining the L would be testing hypothesis of the form H0 L less or equal than L0, and estimate L by means the smallest L0 for which this is not rejected. That means that the component is above, the importance of the component is above the error level. And just remarks to some of the model, of course, if you say the importance that everything is equal to the mean function, then you don't need anything. So L is equal to 0. You don't need any expansions, because all the functions are same, which corresponds to the classical hypothesis of the identical distributions. So everything is the same, which of course in the case of income densities is quite ridiculous, doesn't make any sense. Or for example, if the F is generated by a mixture of two different densities, for example W1 and W2, then of course you see, for example, you could rewrite this F, which is just so a mixture of two different densities where, say, the coefficients of the mixture components change over T. Then you could rewrite this in this form with our model, where the theta would be the T minus T. Okay, that's a normalization. Yeah, so if all FTs are mixture, say, of a small number of L different densities, where the weights of the mixtures change over time, then you always can represent it in that way. Okay, so you see the G would be the difference between the two. The integral of the G's is always 0. Okay, and so that's today's. This model will be fine if you have densities which can be represented as a mixture of a small number of underlying populations, essentially. Well, of course, the components change over time. It's not necessarily the best type of model to consider it directly. For example, if you consider of exponential families of distribution, which you have here, then, for example, instead of f of t, you may analyze log of f of t, the logarithm of the densities. It makes also a lot of sense. Could handle that in the same way as we do. So not directly consider densities, but log of ft. Okay, was also something that, well, there was a discussion in JASA about this paper, what people proposed, and that much better do model logs. I don't know, depends on the application. Okay, so how could you estimate that? How could you estimate the G's and all these things? And of course, what can be done is just you do discretization, right? It's hard to, as Wolfgang said, it's hard to work with something continuous on the computer, and so you use kernel estimates f hat of the f at discrete time points, and then consider these corresponding vectors and consider the resulting eigenvectors, provide an estimates of the g hat of g. Just interpolate them, gives you estimates. In principle, it automatically works. If the discretization, if the m is large enough, you can show that you can get quite close to the g's if you interpolate your estimates there. Or other thing is you may use some Fourier expansion of and use basis expansion and then recalculate that, and this also then allows you to get estimates of the g's. Okay. Just here in this paper we do a little bit of different thing. we consider the dual problem, that instead of the covariance operator, we could consider a T times T matrix, which is of the form, it's just the functionals, ft minus mu fs minus v for different t and s. Yeah, so which are just the integrals over these things. Essentially, it's something like, that's the dual problem. You know? Say something, it's a little bit something like going over from, if you have a matrix X, X transpose, you go over to X transpose X. That's a little bit the same thing. If you want, I can explain in a little bit more detail. And the point is, if you consider this matrix instead of this empirical covariance operator, you can easily show that's a little bit the same. The underlying background is essentially this and this matrix have the same eigenvalues, non-zero eigenvalues. That all the non-zero eigenvalues of this thing are related to the eigenvalues of gamma. So the eigenvalues of this matrix M, lambda 1 larger equal to lambda 2, they are just which are the non-zero eigenvalues of M. Then, if you divide them by T, these are the non-zero eigenvalues of gamma T. Okay? So essentially the eigenvalues of this thing will be T times, capital T times the eigenvalues of the covariance operator. Okay? You should remember this capital T. And also you can recalculate, also if you consider then the corresponding eigenvectors of this matrix, so this is really a matrix, what you get then is just that the eigenfunctions of the covariance operator is just something like linear, what you see here is just linear combinations of the FTs weighted with the eigenvectors of the matrix M. So why do we do that? Essentially, so that this is just some algebra. So if somebody wants, later on we can show you why this helps. It's not really not very difficult. What you see, what the important thing here is a little bit, remember you have to estimate the density, you don't know that. And if you want to estimate this, these type of functions, if they're integrals, integration removes noise in a way. It's like summing. So essentially these functionals are much better to estimate than individual densities at a certain point. But these are integrals which removes variability. So you can estimate this much better than the value, say, ft of x at a specific point. And this eigenfunction, you see that's just a weighted mean of your functions ft. So it's also an average over the ft's. And this combination, you can estimate the p's very well. Can get very nice estimates of the p. And what you see here also here, this averaging over different f's, we remove variance, which has as a fact that also the g's can be estimated in much better, much more accurately than individual kernel density estimates. Okay, so this is essentially the estimation procedure. Oh, I think I have to go a little bit faster now. So what we do in the first step, we estimate the elements of this matrix M using kernel estimate of the ft, and for a kernel function k, we get f hat of t of h, depending on the kernel on the bandwidth h. We just construct kernel estimates of the individual densities for each t. And then, of course, a sensual and natural estimator of this matrix of functionals of this M is just well to integrate over the values of the f hat of t. Except that you make a small, and this is essentially what we do, except that we make a small modification, because if, say, in this case, if I is equal to j, then what you get something that in the diagonal you would get some terms like this, which you see, which has nothing to do in a way, where the true density doesn't come in at all, only the kernel k. And so this creates something like an artificial bias. You have something like so just here where you have diagonals, if the two are equal, t equal to s, you have some additional bias, and you may want to remove this term, because this doesn't add anything. So we subtract this term in the diagonal, and this gives us then our estimate of this matrix M. Where we have here, for the off diagonal, we have just this inner product of kernel estimates. In the diagonal, we subtract this bias term, which has nothing to do with the original density. Okay, so this gives the estimate of the M hat. And from this estimate, then one calculates eigenvalues, eigenvectors. Okay, and the point is that this estimate is quite accurate if you choose a reasonable bandwidth. What we have here is something, the M hat is obtained by summing and integrating over estimates. So what you see here is you integrate over kernel estimates. That's an integration. And so what is done, we have a noise reduction. And theoretically, what you see, the variance of any estimate of the estimate M hat of TS is something like 1 over N, 1 over S, and is almost independent of the bandwidth you use. Just because you integrate over the kernel estimate. And of course, bias does not vanish. So in kernel estimates, you have bias and variance. And so the essential thing is, in order to get good estimates, you should see a very small bandwidth H. For example, H is equal to 1 over N to the 1/2, where N, say, is something like the minimum over all NTs. It's just because you integrate, integration removes noise, but does not remove bias. So choose a small bandwidth, and then you get something. The quality of these estimates of M hat is almost parametric. You can estimate these elements of M hat with parametric quality. And essentially, this is not too new because Peter Hall has already considered functions of these types a long time ago. Should be possible to get through with the main message. Okay, and we can some details. So then we determine eigenvalues and eigenvectors of this M hat, and then using the formula as I showed you above, we estimate these individual coefficients, the thetas, just using the formulas I had some transparencies, prior transparencies, and G hat, but just this local average of the F hat, which is another kernel estimate, weighted with the P hats and the lambda hat. So just with the estimated eigenvectors and eigenvalues of the M matrix. And F hat is another kernel estimate with a bandwidth B, which is usually not equal to H. The important thing to get good estimates here is H very small, because of this noise reduction in the functionals, small bias. B must be larger in order to have not too much variance, in order to avoid strong variability. So you have two different bandwidths, which is unfortunately necessary in this context. Well, okay, some asymptotic theory. I don't want to discuss that now. I have not the time to say a lot of it. Some assumptions, some regularity conditions. It's important always, if you want to do some theory in this case, that you assume all eigenvalues are not the same. You are all different, multiplicity 1 for all eigenvalues, otherwise you have some problems in this context. These are some results about these M hat estimates. I don't want to discuss them.
So M hat is the estimate
of this dual matrix, yeah, where we determine eigenvalues and eigenvectors just with these functions. Yeah? So, but that's the more important qualitative results. When you get something, so the expectation of M hats, so that's the bias term, is of order, well, there should be, the absolute value is missing here, is of order H squared, as usual for kernel estimation, because we consider functionals, but bias does not integrate out. Variance integrates out, but not bias. Whereas the variance of M hat TS minus the variance of these things is just of the order 1 over N, essentially independent of the bandwidth. It doesn't depend on H. So what's the thing is, choose H small. Which H is very small, that the bias is of the same order of magnitude as the variance. So something like H is equal to N to the minus 1/2. That means individually it's a big undersmoothing, because an optimal bandwidth to estimate the density is to the order N to the minus 1/5. If you have twice differentiability, that's what I assume. Whereas for these functionals, it's make a much smaller order, much smaller H, which will produce very wiggly estimates, but by integrating all these functionals, this variance cancels out. Okay, so very small bandwidth in this case. And if you have something like, and the usual bandwidth for estimating individual densities will be the order N to the minus 5. Well, straightforward method way, just multiplied by a term that gives you here the right order of magnitude.
Okay, suppose you use a series estimator for the density.
Well, and then it would, series estimator is essentially the same thing. Then the number of components you use is your smoothing parameter. Okay, these are the results now for the eigenvalues, eigenvectors. These are results for the g's, how the g's are estimated, and that you have something that is asymptotically normal. This is bias, depends on the second derivative of your, I suppose these are differentiable, okay, of the g's, and b square is the bandwidth we use in the second step. I have h for the M matrix, b for estimating the g's. And this is the variance of these things, which depends, we say here, in the denominator you have the b, the bandwidth, and the n, the number of observations per curve. Also this thing, because lambda squared is of the order t. So this also goes down to the number of coefficients. Okay? So these are essential results. Just for bandwidth shots with the b, perhaps this result is easier to interpret. What you get something, the MIZ of G hat R, is essentially something, a bias term, which is the order b to the power of 4. That's the bandwidth we use in this estimation step. Plus 1 over n TB. What you see a little bit, there are two things coming in. N is the number of observations per year, for example, for the incandensities. T is the number of curves you have, so the number of years you have. And B is the bandwidth. So the difference from individual estimation, if we estimate separately the density for 1 year, the T is not there. Yeah, you have 1 over NB, number of observations, time in the variance for kernel estimator with B. So what you here see, essentially because the variance also decreases with the number of curves you have, with the T. And so you get back much better estimates of the G here than of individual densities. You have better estimate than individual densities. It also depends on the eigenvariances, okay? And the optimal bandwidth here is of the order nt to the minus 1/5. So it goes down with t too. T is the number of curves you have, yeah? The number of years. And the reasonable bandwidth for estimating densities will be something for individually, the cross-validation will give you a bandwidth to the order n to the minus 1/5. You know, well, you may, but this has to go down with t2, so you may multiply it with 2 to the minus 1/5. And so what you see, so the essential methods here, G hat, estimates of G hat are much better than individual densities. Okay, you could also develop a plug-in method from that. I don't want to talk from that. I also can re-estimate individual densities from that. Okay, I just forgot the F mu here, the mean. Okay, sorry. So we have something like F is the mean plus these things, and then you have F hat, and then you just use your estimated versions. And what you can show a little bit, if now here is a qualitative assumption that this goes up to a fixed L, this is that the L is not equal to T, but a fixed L, then what you can show a little bit, that essentially this, the F hat, the re-estimated individual densities, is of the order of magnitude n to the minus 1/2 and t to the minus 2/5, which means essentially it's much better than the usual non-parametric rate of convergence from your estimates. It's just because you get the G's better and the thetas just depend on n, a square root of n consistent. So essentially you can improve your individual estimates by using by just using information from all the sample, and the fact that the other densities also give information. By the point is the G's are estimated from all densities, from all years, and so you get more precision. And this precision then also helps you to re-estimate the individual densities by using information from the other years. So you get much qualitatively better estimates. And then test of dimensionality would be how big is L? Is a little bit, the idea is theoretically, if the hypothesis L smaller than L0 is correct, then the sum of the last T minus L 0 minus 1 eigenvalues is 0. And so the test statistics is just this row hat is this sum here of the smallest eigenvalues, and you have to reject the hypothesis that the two-dimensional L0 if row hat is too large, otherwise it's too small. And we have theoretical results about it. Usually rho hat is normally distributed. What we use here to determine these things is a bootstrap procedure using the reconstruct individual curves with L0 components. Of course, this then is an L0 dimensional system of densities. And this if H0 is true, these things should be fairly close to the true family of Ft. And then for each t, we mimic the data generating process by resampling IID observations from these estimated densities. Then we get the m hat star and estimate eigenvalues lambda star, re-estimate the whole method, and this gives then a value for the smallest t minus L0 eigenvalues. And from the resulting distribution, we get critical values, and we can show this bootstrap is consistent. So, and this test is also valid for L0 is equal to 0, which corresponds to the hypothesis all densities are equal. Just to show you just to finish, show you a little bit of application to this income densities from Great Britain. You see here the densities for the different years, and essentially we used here something like 20 years. And you see how the eigenvalues decrease. From the dimension test, we said something, this is the dimension test, that essentially the hypothesis, there are 3 components necessary. It's not rejected. This was not true for H densities, there you need a lot. And just to interpret these things a little bit, what you see here are the first and second principal components. So this one is G1, this is G2. You see, this has not much to do with sinus functions, or something like that. That's not Fourier representation, no? Well, you need a lot, huh? 6, I don't know. You need a lot. Okay. So this is the development. These are the G1. This is G1, G2, and this is a little bit of time series of the theta 1 G. So the component score for the first principal component. You see essentially the theta 1, it has something like an increasing trend. It goes up over the years. And just to the theta 2 here, well, it's very hard to interpret. What does it do? And for example, what you see here is a little bit, we showed these little bit of deformations. How do the densities change over time? And we just here interpret the first principal component. What does it do? What does it do? How do the densities change in this case? And just to represent that, we consider deformations. That is for every year t. That was the basis here, 1968. We just consider G1, the first principal component, and then the value theta hat T1 minus theta hat 1968. So you see for t equal to 1968, that's just the 0 line. Right? For 69, well, that's just theta hat minus 1969 minus 68 G1. This gives then how does the density from 69 a little bit differ from that in 68, at least concerning the first principal component. Now, if you remember that the theta hats for the first principal component, they generally increase over time. What you see here, for example, 68 is this small thing. And for example, here they are the 80s. Yeah, these are the big ones. So essentially, here it's an increasing over time. This is something like 68, 69. This is 80, 82, 84. Okay. So what you see, what does this thing do to the density? How do they change the original density at 68? So what you a little bit see is there are some effects here. For example, here's the means. That is just the mean income, and you see here it subtracts, it's minus. So that means there is less mass here around mean income, just in the middle of the population. So in a way, relatively, in later years, there are fewer people which mean income. Yeah, which income are mean income. On the other hand, here there's a lot more people with incomes around 0.5, half of mean income. So rather poor people. Yeah? And there are also here a little bit more people who have really considerably more. It's also a little bit less the extremely poor. Yeah? A little bit less the extremely poor. But the essential effect is a little bit, there's mass out of the middle into poor and into rich. So it's a little bit something like an increasing inequality, what you see here. Okay? For this income debt. Once they have the student has done the same thing to German income densities from 90 to from 1980 to now, and there it's much different. Also, we had to cut these things in different periods, and for example, after the reunion, before the reunion, German income densities are less complex. Only one peak, for example, not several peaks as the English ones. And also there was a very different tendency. There seemed to be a tendency towards more equality, less inequality, say in the early 90s, in the 80s. And later on, from the year 2000, very strong effect of increasing inequality. It was a really different story. Okay, so So thanks, that was the first talk, already very long talk. Okay.